Okay, so I got a 90-pound toboggan slash rider heading down this slope, given this equation, as we all take the equation of any slope we ever sled down. Okay, when x equals 10, I know the speed is 5 meters per second. Okay, uh, we want to find the rate of increase in speed and the normal force exerted on the toboggan. Okay, so here's what we've got. We're going to draw a free body diagram. Okay, so I've got my sled right there. Okay, we know we have 90, that'd be kilograms, so that's going to be 90 times 9.8. That's the toboggan and the kid going like that. The other thing that I know I have is a normal force in this direction, and I'm trying to figure that out. Okay, now I'm trying to figure out my tangential acceleration, which would be like that. And again, this guy's going around a curve here that I have an equation of, so I should be able to find the radius of curvature. So I'm going to have my normal in that direction, right? Set up my coordinates like this. Again, I'm trying to find the rate of increase in the speed. So that by definition is my tangential acceleration. I'm also trying to find that normal force that I have going on right there. Now, the tricky thing here is I need to find essentially this angle right here that I'm going to call theta. Okay. What I am looking at is I am going to find this slope, right, which would be rise over run of this guy, right? So that is effectively this angle right here. It's the same theta. Okay. So we're going to find that. And again, I'm going to find that using the slope of the line, which I'll just do down here, dy dx, right? Where the equation of the line is 0.08x. So that then becomes 0.16x. And when x equals 10, the slope is 1.6. And again, by definition, this is the rise over the run, which I can equate to the tangent of that angle. So the tangent of that angle equals 1.6, again, because dy dx is change in y over the change in x, right? Which is going to be the opposite over the adjacent. And then from that, I can find then that my theta is going to be 58 degrees using that. So I find that angle right there. Okay, so now that I know that angle, let's go ahead and start applying uh, my equations here. Okay, my equations of motion. So I'll sum the forces in the tangential direction. The only force I have in the tangential direction is the sine component of the weight, right? And the weight is 882. Again, that's 90 times 9.8 times the sine of 58. Okay, and that is going to equal, again, the tangential acceleration times the mass. So that's 90 times the tangential acceleration given like that. Okay. Go ahead and do the same thing in the normal direction, where I'm going to get the normal force that I'm trying to find minus, this would be cosine of that 882. So 882 cosine of 58. And that's going to equal my normal acceleration, which is going to be 90, that's the mass, times the normal acceleration, which will be v squared, which is given to us as 5 all over rho. So now I need to go figure out rho, where I use the equation again because I was lucky enough to know the equation for the slope here. I can find rho equal to 1 plus the first derivative squared to the 3/2 power divided by the absolute value of the second derivative. So I need to take 2 seconds, find the second derivative, d squared y dx squared, which then is just going to be 0.16, very simply. Plug what I know, the 1.6 and the 0.6, into this equation, and I can find rho is 41.98, which I can go ahead then and plug up into this equation 41.98. Okay. Now, very simply, I've got two equations, two unknowns, and really each equation is independent of one another. So I can find my tangential acceleration. This is the change in speed is going to be 8.31 meters per second squared. Okay. And then from the second equation, I can easily find my normal force, and then normal force is going to be 521 newtons, which is fine. So again, draw your free body diagram, recognize what kind of acceleration you have. This would be normal and tangential, knowing that I have the equation of the line so I can find the angles. I can find the radius of curvature at the instant that I'm interested in to help me figure out my my normal acceleration and that sort of thing, and then apply your equations of motion and solve.